Hello, welcome to another video of thermodynamics. In this video, we're going to talk about isentropic processes of ideal gases. Basically, we're going to look at how to analyze an isentropic process of an ideal gas. There are two methods of analysis in here. So first of all, we write isentropic processes of ideal gases. Isentropic process is a process where entropy remains constant. In that case, we can actually analyze this situation in two methods. One is called the approximate analysis. That's also called constant specific heat. And called the second one is exact analysis. It's called the variable specific heat. Specific heats. First, we'll look into the approximate analysis. Or constant specific heat analysis. So in this case, we take those two equations that deal with entropy change in approximate analysis. S2 minus S1 equals CV natural log of T2 over T1 plus R natural log of V2 over V1. Just because since this process is isentropic, that means there's no entropy change, so we know that S2 is equal to S1 during the process, right? Therefore, your left hand side becomes 0. May write it in here. You can write it in here. 0 equals CV natural log of T2 over T1 plus R natural log of V2 over V1. From this, we can obtain that ln CV ln T2 over T1 equals minus R natural log of V2 over V1. Now, if I divide this by CV, entire equation, ln T2 over T1, so R divided by CV, let me remove that part. R divided by CV. So this is R. It's always taken as a triangle. R divided by CV ln V2 over V1. And by using logarithmic rules, I can take this as a exponent, right? So this is natural log of T2 over T1, and I'm going to take this R over CV as an exponent. And by flipping the V1 and V2 switching V1 and V2, we can make this negative a positive. Natural log of V1 over V2, I switch this R over CV. And by taking the anti-log of this either side, I can say T2 over T1 equals V1 over V2 to the power R over CV. And from CP and CV, CP over CV equals K. This is called specific heat ratio. And we also know that R, gas constant, is equal to Cp minus Cv, right? And we had R over Cv in the previous equation, R over Cv. So instead of Cp, I'm going to substitute Cv. R equals K times Cv minus Cv. From that, you have Cv K minus 1 equals R. And then R over Cv is equal to K minus 1. So from the previous derivation, we got T2 over T1 equals to V1 over V2 R over CV, R over CV, R over CV. Now R over CV is equal to K minus 1. So I can write T2 over T1 equals V1 over V2 to the power K minus 1. Now that's the one relationship. Now by using PV equals RT, ideal gas law, ideal gas equation, I can substitute V in terms of the other variables. So I can get T2 over T1 equals, instead of V, I can say from this, I can say V is equal to RT over P. So I can put RT1 over P1 divided by RT2 over P2 K minus 1. R is a constant, so that cancels out. And then you have P2 over P1, and then this is going to be K minus 1. And also we have T1 over T2 K minus 1. And this is T over T2 over T1 sit. And I can divide this this side by T2 over T1. So this is T2 over T1, 1 minus K, right? 1 minus K. And then so I can take this into the other side. In that case, I get T2 T1 times T2 over T1 K minus 1, right, equals P2 over P1, sorry, P2 over P1 to the power K minus 1. So when you add up the indices or the powers of the same base, right, exponent of the same base, you get T2 over T1 1 plus k minus 1 equals P2 over P1 k minus 1. So you get T2 over T1 to the power k, and if you get the kth root of this, you get P2 over P1 k minus 1 over k. That's the second equation. So we got one equation here and one equation there, and you can also derive that another equation, right, which can be derived by the first equation by replacing t in terms of p, right, and I'm not going to derive that. I will explain it here. I can write first one, we got T2 over T1 equals V1 over V2 to the power k minus 1 k minus 1, and we have the second is T2 over T1 equals P2 over P1 to the power k minus 1 over k, and third, the last one, P2 over P1 equals V1 over V2 to the power k. These all can be used for an ideal gas, isentropic process of an ideal gas under the approximate analysis or constant specific heat analysis. Now if you move on to the exact analysis, we move to exact analysis. In the exact analysis, we figured that S2 minus S1 equals S20 minus S10 minus R natural log of P2 over P1. For an isentropic process, S2 minus S2 equals S1. So that means this side, left hand side, is equal to 0. 0 equals S2 naught minus S1 naught minus R natural log of P2 over P1. Okay, and then we get R natural log of P2 over P1 equals S20 minus S10 minus R. S20 minus S10. Then from this equation, we can say that P2 over P1 equal S20 minus S10 divided by R. So that's natural log of. To remove the natural log, we get the exponential. So when you get the exponential of natural log, that becomes P2 over P1. The other side, exponential of S2 naught minus S1 naught divided by R. Now, this can be written as e to the power, so exponential is e to the power, or exponential of S2 naught over R divided by exponential of S1 naught over R. and this is P2 over P1, P2 over P1 equals to, this is called the relative pressure, that's called PR, PR2, PR1. Now these PR values can be found from tables, any standard ideal gas tables. If you know the temperature of the fluid of the ideal gas, you can find this PR2 and PR1. And then there's a similar equation. You can change that P to V, right? And then you can, by using the ideal gas equation, you can use P to V, change P to V using ideal gas equation. In that case, you can get V2 over V1 equals to VR2 over VR1, right? So that's the second equation for the exact analysis, and here also relative volume, relative specific volume VR can be found from the table. Okay, that's it about uh, the derivation of isentropic processes of ideal gases. What are the equations that we can use, and what are the limitations? So I would hope to see you in another video. Thank you very much.